Hi everyone, this is K. Karthik from Institute of Aeronautical Engineering from Tripoli Department Section A. My roll number is 23951A0206. Now we are discussing about distribution of the product of a complex Gaussian matrix and vector and its sum with a complex Gaussian vector. In this presentation, we all analyze the impact of complex Gaussian matrix vector multiplication and summation with complex Gaussian vector. In product distribution, we will provide a comprehensive analysis of the implications and applications of these operations in various fields. The distribution of the product of complex Gaussian matrix and a complex Gaussian vector is not a simple one, and it depends on the properties of both the matrix and the vector. The distribution of the sum of these product and another complex and Gaussian vector is even more complicated, and it requires some advanced mathematical tool derived. Understanding the properties of complex Gaussian matrices is crucial for analyzing their impact on vector multiplication and summation. These matrices exhibit random elements with real and imaginary parts following a Gaussian distribution. Fortunately, there is a paper that addresses this exact problem and provides the exact probability density function and cumulative distribution functions for both the product and the sum. The paper is titled Distribution of the Product of the Complex Gaussian Matrix and Vectors and its Sum with a Complex Gaussian Vector. Vector multiplication. The multiplication of complex Gaussian matrix is vectors, involves intricate calculations and yields complex Gaussian vectors as results. This process has significant implications and statistical analysis, signal processing, and communication systems. Vector multiplication is a mathematical operation that involves multiplying two or more vectors by a scalar or by another vector. There is different types of vector multiplication, such as the dot product and cross product, the exterior product and the handmade product. Each type of vector multiplication has its own definition, properties, and application in various fields of study. The dot product of two vectors is a scalar quantity that measures the cosine of the angle between them. It is also called the scalar product because it is reduces the vectors to a singular number. The dot product can be used to define the projection of one vector onto another, the angle between two vectors, or the work done by a force along a displacement. The cross product of two vectors is a vector quantity that is perpendicular to the plane containing the two vectors. It is also called the vector product because it produces a new vector from two vectors. The cross product can be used to find the area of parallelogram and torque exerted by a force, or the angular momentum of the rotated body. The exterior product of two vectors is bivector quantity that represents the oriented area spanned by the two vectors. It is also called wedge product because it uses the wedge symbol to denote the operation. The exterior product can be used to define the concept of differential forms, which are useful in calculus and geometry. Summation analysis. The summation of complex Gaussian vectors leads to the generation of new complex Gaussian vectors. This operation plays a crucial role in probability distribution, random processes, and data analysis, influencing numerous scientific and engineering applications. Summation analysis is the process of studying the properties and applications of summation notation, which is a cosine way of expressing the sum of a sequence of numbers. Summation notation uses the symbol, which is the Greek letter sigma, to represent the sum of series of terms. The terms can be defined by a formula, a function, or a set of data. Summation notation has several components, such as the index of summation, the lower limit, the upper limit, and the general term. Summation analysis can be used to find the value of all sum, to simplify or manipulate a sum, to prove a disprove a mathematical statement involving a sum, or to apply a sum to a real world problem. Product distribution. The impact of complex Gaussian matrix vector multiplication and summation with complex Gaussian vector on product distribution is profound. This analysis provides insights into the statistical behavior and characteristics of the resulting distribution. Product distribution according to the matrices is a topic that involves the application of matrix applications and its properties to the problem of distribution, the product to differ markets and customers. Matrix multiplication is a multiplication operation that involves multiplying two or more matrices by a scalar or by another matrix. Matrix multiplication has some properties that are similar to those of real numbers, such as associativity, distributivity, and linearity. But it also have some properties that are different, such as non-commutativity, non-cancellation, and non-invertibility. One of the application of matrix multiplication and its property is to model the distribution of product from the producer to a consumer through one or more intermediaries, such as wholesaler, distributor, or retailer. Applications in signal processing. The comprehensive analysis of complex Gaussian operations has wide-ranging applications in signal processing. These operations influence the behavior of signals in noise, channel modeling, and wireless communication systems. The implications of complex Gaussian operations on statistical analysis are significant. Understanding the impact of these operations is essential for modeling random phenomena, estimating parameters, and analyzing experimental data. Communication systems impact. Complex Gaussian matrix vector multiplication and summation with complex Gaussian vector have a sustainable impact on communication system. These operations influence the performance of wireless networks, digital modulation, and error correction techniques. Challenges and opportunities. The comprehensive analysis of complex Gaussian operations present both challenges and opportunities in various scientific and engineering domains. Understanding these complexities is essential for leveraging and potential applications of these operations. Future research directions. Exploring future research directions in complex Gaussian operations is crucial for advancing scientific knowledge and technological innovations. This analysis sets the stage for investigating new applications and theoretical developments in this field. Key findings. The key findings from our comprehensive analysis of complex Gaussian operations provide valuable insights into their impact on various scientific engineering and mathematical disciplines. These findings contribute to the advancement of knowledge and applications in these domains. Conclusion. In conclusion, the analysis of complex Gaussian matrix vector multiplication and summation with complex Gaussian vector reveals their profound impact on diverse fields. Understanding the implication and application of these operations is essential for advancing scientific knowledge and technological innovations. Thank you.